All right, AP Chemists. This is still part of our summer work important information part 4. This is our 4th lecture. This is our last big topic in this unit and probably the last toughest calculation that you'll learn for the summer. This is going to be the toughest and most involved type of calculation that you'll see involving stoichiometry all year. A lot to consider. It's known as limiting reactant. And so we are going to probably spend like a 2-part here. I'll probably do an analogy with sandwiches and then do an example and then have you try the conceptual limiting reactant and theoretical yield number 1 and leave it at this for this video. And then in my next and last video of this unit or this part, I'll work with doing these type of calculations with a BCA table and end with just you doing some practice. All right. Also, if you were doing some of the exercises from the previous lecture, I did completely answer question 12 for you. So if you wanted to pause and get the answer here, you should get that you needed 55.9 grams of Ki as your reactant to start. I used the BCA table. You should also get that you needed 0.168 moles, or you will make 0.168 moles of PBI2 and 0.337 moles of KNO3. So you could use this to either correct or check your answer to question 12 for the previous lecture that exercises that you had to turn in. All right, so without further ado, we got stoichiometry, limiting reactant, theoretical yield, percent yield, and reactant in excess. I just want to talk through each of this vocab here. So you're going to see a limiting reactant or a limiting reagent is the reactant that is completely consumed. I use all of it. It goes to 0 in the end in a chemical reaction, and it limits the amount of product that can be made. If I have a bunch of reactants together and there is that one reactant that is stopping me from making more products, we call that the limiting reactant. I'm going to use that analogy with sandwiches, right? Like if you're making a sandwich and I need 2 slices of bread and I only have 1 slice, well, I can't make a sandwich, or the bread is limiting how much sandwiches I can make. Then you have your reactant in excess, which is what it sounds like. It's going to be the reactant that we have extra of. The theoretical yield, this one's tough, is the amount of product that can be made. And it's based on the amount of the limiting reactant. So how much product I could make in a reaction comes from the limiting reactant, the one that limits how much product can be made. Then we have something called the actual yield. I'm going to let you know that's something that you're told, you're given, or you measure in an experiment, right? It's the amount of product that you actually get. Not all times will the product that you should get is going to be the same quantity that you actually get, and it's because of human error or things with the experiment. And now that I know what actual yield and theoretical yield, you could do something called percent yield, which is calculated as actual divided by theoretical times 100. I'm going to say 100, not 100%. And that's going to give me my percent yield. So let's say I was supposed to get 50 grams is my theoretical, and I actually get 25 grams. Like I find out that in my reaction mixture, I only get 25 grams of my product. My percentage would be 25 over 50 times 100. That's 50% yield. Just as a quick little random calculation. Now, I thought it best that before I get into the ugly of stoichiometry, that I use an example that we may all be familiar with, which is making sandwiches. So let's look at a little bit of a sandwich analogy here, okay? So let's say Mr. T is making one of his favorite sandwiches, like I'm just going to say a meat and cheese sandwich, and let's say the meat is bologna, but I didn't want to write the word bologna, too many letters here. So my sandwich requires 2 pieces of bread or 2 slices of bread to make one sandwich. I need 1 slice of meat to make that one sandwich, and I need 1 slice of cheese to make that sandwich. And let's consider this kind of like a before and after in a chemical reaction. Let's pretend like the sandwich is a chemical reaction here. So 2 slices of bread, 1 meat, 1 cheese, and I get 1 sandwich. So 2 bread, 1 meat, 1 cheese, 1 sandwich. I don't have anything left over. It doesn't look like there's anything that's limiting. This is a complete reaction. Complete reaction. There's no leftovers. And I don't have to worry about what's known as a limiting reactant. But what if I have quantities of my bread and my meat and cheese that are not in this beautiful 2:1 ratio? What if I had 2 pieces of bread, 2 meat, and 1 cheese? How many sandwiches can I make? Well, for a sandwich, I need 2 pieces of bread, 1 meat, and 1 cheese. This is going to help me make my 1 sandwich here. But it looks like I have 1 meat that's left over. We call this leftover meat the excess reactant. It's left over, it's not completely used. It looks like my bread and my cheese here, my bread and my cheese here limits how much or how many sandwiches I could make. My bread and cheese limit how many sandwiches I could make. Because they follow that 2:1 ratio, right? I have 2 pieces of bread, 1 cheese, that's good, but I have too much bologna. So I would consider my bread and my cheese as my limiting reactant, right? So bread and cheese would limit how many products I could make. 2 bread, 1 sandwich. 2 meat, if I had 2 meat and enough bread and cheese, I could make 2 sandwiches. Why is it... Sorry, typing it wrong. 2 sandwiches. If I had all the bread and all the cheese that I possibly can have, if I had 2 pieces of meat, that could give me 2 sandwiches. If 1 cheese would be 1 sandwich. And this is what I mean by your reactant would limit how many products I could make. My 2 meat are not going to be limiting because it makes too many products. Or too many sandwiches as my products. I'm only going to be able to make 1 sandwich because the bread and cheese is stopping that. Now, what if I do another one? What if I had 6 bread and 3 meat and 3 cheese? Well, I know that for every 2 bread, I'll get 1 sandwich. If I had 6 bread, that's times by 3, that would give me 3 sandwiches. Let's look at the 3 meat. If I have the 3 meat, well, I know that 1 meat is 1 sandwich, according to the ratio. If I had 3 meat, I get 3 sandwiches. And then do the cheese. If I had 1 cheese, I'd get 1 sandwich. 3 cheese would be 3 sandwiches. And look at this. I get the same amount no matter which reactant I'm using. And that's because this 6:3:3 ratio is and can be simplified to 2:1:1 ratio to give me my 1 sandwich. 6:3:3 is the same as 2:1:1, and that is my ratio according to my balanced sandwich equation here. And look at this. I get exactly 3 sandwiches. Completely. With no leftovers. So why am I showing this? Well, the quantities in a balanced chemical equation is going to help me figure out how many products I could make. If those quantities are not in the same ratio as the given coefficients in a balanced chemical equation, I'm probably going to have a limiting reactant. So look at this one. This ratio was 2:2:1. That is not the same as 2:1:1. So I'm dealing with some sort of limiting reactant type of situation where I have to figure out which part of my reaction or which part of my reactants are going to limit how many products or how many sandwiches I could make. I'm going to kind of erase this, and I just want you to kind of look here. You don't have to worry about copying what I'm doing right now, but what if instead I only had 1 piece of cheese? So you could just listen to this. What if I just had 1 piece of cheese? How many sandwiches can I make? right? It would not be 3. If I had 6 bread and 3 meat, but only 1 slice of cheese, it might be obvious which ingredient here is going to limit how many sandwiches I could make. This cheese, this 1 cheese, limits how many complete meat and cheese sandwiches I could make. I could only make 1 sandwich if I have that 1 cheese. I can't make 2. So with that being said then, I'll use the 2 bread, the 1 meat, and the 1 cheese. And these 4 slices of bread and these 2 meats are going to be left over. They can't be used to make a complete sandwich, and I would consider them my excess reactant. So this was just a random other example that was kind of similar to the one where I had 2 bread and the 1 cheese, but this time I only had 1 limiting reactant. If I only have 1 slice of cheese, then I could really only make 1 complete sandwich. The same could be said if, let's say I only had 1 slice of meat. So let's say I don't have this meat, and I have these 3 cheeses. If I had 6 slices of bread and only 1 meat and the 3 cheese, well, that meat is going to limit how many sandwiches I could make. And I'm going to have 2 pieces of cheese left over and 4 slices of bread left over. So I'm hoping that you didn't get a little hungry as I was doing this analogy, but I wanted you to think about making complete sandwiches. The analogy here is a sandwich is kind of like a product in a chemical reaction. Your ingredients are kind of like your reactants. So we're going to do an actual chemistry example now with a chemical reaction. And I'm going to have you thinking about this idea of sandwiches and bread slices and cheese. And you're going to tell me which reactant, which ingredient is going to limit how many sandwiches or products I could make. So let's do an actual stoichiometry example. So we can apply these concepts to a chemical reaction. Recall our balance equation for the combustion of methane right here. If we start out with, I change this to 5 moles of CH4 and 8 moles of O2, what is our limiting reactant? Let's answer that first. What is our limiting reactant? So to remind you, our limiting reactant is one that will limit how many moles of products can be made. It will produce the least moles of product. So let's do mole ratio kind of dimensional analysis calculation to see which of these substances is going to limit how many products are going to be made. Let's just arbitrarily, it looks like the second question is, what's our theoretical yield of carbon dioxide? Let's look at carbon dioxide. Okay, so for every 1 mole of CH4, I will get 1 mole of CO2. For every 2 moles of O2, I will also get 1 mole of CO2. Well, in this case, I have 5 moles of CH4. If I had 5 moles of CH4, you could see clearly that this is a 1-to-1 mole ratio. For every 1 mole of CO2, there's 1 mole of CH4. So if I completely am depending on CH4, if I'm depending on CH4 alone, I will get 5 moles of CO2. But what about O2? This is a 2-to-1 ratio. I will get half the amount of CO2 than I do O2 have. So I'm going to probably divide by 2. So I have 8 moles of O2 times 1 mole of CO2 for every 2 moles of O2. And I will get 4 moles of CO2 if I was depending only on O2. If I look at both of these answers, I have to ask myself, which of these is going to limit how many moles of product can be made? Which substance is limiting how many moles of product I could make? And you're going to answer and say, well, my O2 gives me my least moles of product. So my O2 is limiting. or is the limiting reactant. If O2 is limiting, that means I'm not going to get 5 moles of CO2 from the 8CH4. This means my CH4 is in excess. And we could show calculations about that later. So now I know that I am making 4 moles of CO2. My limiting reactant is O2, and I'm going to make 4 moles of CO2. That is my theoretical yield. Now, of course, the molar mass of CO2 is 44 grams per mole. And we've done that in a previous problem. If I want to know how many grams that is, I will do 4 moles of CO2. Remember, moles times molar mass is equal to grams. If I multiply by the molar mass, 4 times 44, I get 176 grams of CO2 that can be produced from that 4 moles. This is what I call my theoretical yield. Okay? So, look at where my theoretical yield came from. It came from the amount of moles that my limiting reactant can give me, the smallest moles of product. So now I have what's my limiting reactant, I have how much of my product I could make, and I actually just converted that to grams by multiplying by the molar mass. And then finally, percent yield, as I mentioned on the previous page, is actual over theoretical times 100. Well, in this question, it says if 55 grams of CO2 were recovered, what is the percent yield? Well, actual is the 55 grams. Theoretical is what I just calculated, what I should get from my limiting reactant, 176 grams. If I divide these two, 55 divided by 166, and I multiply by 100, I will get 31.25% yield. Boom, done. So this was just an oversimplified problem here, but this is the concept. This is how we do limiting reactant problems. Now, I didn't mention it, but how will I know I have a limiting reactant problem? Limiting reactant problems give you 2 or more reactant quantities. Reactant quantities. It would be very important for you to remember that. I know that this is a limiting reactant problem because I gave you an amount of 2 reactants. If I only gave you the amount of O2, or if I only gave you the amount of CH4, this would not be a limiting reactant problem, and we would solve it like in our previous video. We're going to do more calculations like this in our next video. I just wanted you to get all set up here. What I want you to think about now is conceptually understanding limiting reactant and theoretical yield, and you're going to submit your answer, this multiple choice answer here, as credit for this lecture. This is going to go back to sandwiches now, but instead of sandwiches, we have actual molecules. So here's our balanced chemical equation. For every 1 mole of N2, I need 3 moles of H2. So I'll make N2, H2, and I will produce 2 moles of NH3. And we've balanced this equation in a previous lecture. All right, so here's my balanced chemical equation. If a flask contains a mixture of reactants represented by the image below, so it looks like I have 1, 2, 3, 4, 5, 6, 7. It looks like I have 8 H2. We can consider each of these a mole. So I have 8 H2 molecules, which we could say, all right, let's say I have 8 moles of H2. And then I have 1, 2, N2. I have 2 N2 molecules. Let's just say I have 2 moles of N2. Which image below best represents the mixture in the flask after the reactants have reacted as completely as possible? What is the limiting reactant? So I'm going to ask you to write that down to answer this. So you're going to write down what is the limiting reactant here. and which reactant is in excess. You're going to write that down here. You have two choices, N2 or H2. I want you to think about the sandwiches here. It looks like for every 1 N2, I could get 2 NH3. And it looks like for every 3 H2, I also can get 2 NH3. Which of these is limiting how many NH3s I could make? Is it the N2 or is it the H2? And if that were the case, how many NH3s could I make? And which reactant is in excess? In the next lecture, I'm going to pick up with giving you the answer to this, and then we'll do more calculations with limiting reactant, theoretical, actual, and percent yield calculations. So remember, you are just turning in your answer to this conceptual limiting reactant and theoretical yield for credit.